everyone. I think I know everyone here. I'm Tara Rizzi with AIA Santa Barbara. And we have our webinar today on presented by Taylor and Saifan on earthquake prevention. Sage Shingle is the project manager there, who is our presenter. We will be gathering questions in chat box throughout the presentation, so feel free to do that, and they'll be addressed at the end. So over to you, Sage.
Okay, great, thanks. I think one just real brief point of clarification on that, Tara. Thanks for the introduction, but we're not going to talk about earthquake prevention today because that's a huge task that I don't think any of us can possibly actually do. But we're going to talk about earthquakes and a reaction to them through history of California. So with that in mind, let me share my screen and we'll move on. Okay, so like I said, history of Santa Barbara earthquakes, building codes, and how it can apply to your next renovation project. So we'll talk about Santa Barbara earthquakes in particular, and then California's kind of most devastating earthquakes, and then how that relates to historic building codes and moving into current design, and what that's done with our building materials over the years. We'll concentrate that on residential structures just because there's a ton of different things that we could get into, but for the sake of this, we're going to simplify and just do some residential. And then, just some things to kind of be aware of and think about when talking with clients or thinking about your next renovation project. So just about me a little bit. So I grew up here in Santa Barbara. I went to San Marcos High School. I went on to Cal Poly San Luis Obispo, got my degree in civil engineering. And then from there, I moved down to San Clemente and worked for about 4 years doing primarily like 90% school work. After that, I moved up to Seattle. And I did quite a bit of different interesting engineering work up there. I still did a lot of schools. I did public projects. I did some large high-rise buildings. I did some docks, all sorts of different kind of interesting and fun stuff. While there, my wife and I also had 3 kids. And about 5 years ago, we moved back to Santa Barbara. So now we're here in Santa Barbara building bamboo structures on the beaches across the area. Throughout, I've been the last 14 years, I've been involved with this ACE mentor program. I'll just touch on that a little bit later, but tuck that away. And I need to acknowledge Kate Robinson, who was an intern for us this summer out of our Pasadena office. She goes to Cal Poly San Luis Obispo as well. She's doing architectural engineering, and she did the heavy lifting in terms of putting together this presentation and finding great images and a lot of work that she did. So I definitely have to give her some acknowledgement and thank you. Okay, so just starting real briefly, and again, I'll point out that 2 things. One, if you've got questions or comments, awesome, put them in the chat box and we'll talk about them at the end. Hopefully this stirs up some sort of questions for you guys or some sort of takeaways. And 2, I'm kind of far from a geology expert, but I do know, a bit about earthquakes. So I'm going to transmit as much of that as I can to you guys. And here goes. Okay, so earthquakes, this is kind of showing a few different things that are the keys to an earthquake. The depth of the earthquake, the distance to the epicenter, are big components of how much shaking we actually feel at a site. And that fault rupture, the yellow line there, the fault is obviously not just a two-dimensional line on a map somewhere. It's three-dimensional, moving all over the place, and how much that fault ruptures, whether it's grinding a slip fault along its kind of axis, or if it's a diving kind of action that one plate goes under the next. That as that ruptures, energy is released, and we feel that in the form of an earthquake. So the shallower the depth, the closer the distance, the more you feel it. So the couple different ways that people talk about earthquakes are the Richter scale, which is generally what's reported in news, and then this modified Mercalli intensity scale, which is kind of how geologists and engineers kind of track the intensity. In general, in that 3 to 4 range is when you start to feel earthquakes. Below that, and you don't even notice that they're there or they're happening. And then we get up to the 5, 6, 7, and you start to see some damage. Obviously, the higher we get, the more damage you get, the more shaking. And looking at this, there's a couple things that that are a little bit misleading or difficult to kind of understand about earthquakes. One is, this magnitude on the left, that's the Richter scale. And as you go up a notch every time, from a size 2 to a size 3 to a size 4 to a size 5, 2 to 3, a 3 is 10 times the magnitude of a 2. Going from 4 to 5, a 5 is 10 times the magnitude of a 4, size 4 earthquake. And that's actually like physically the magnitude of the seismograph as it monitors and records the shaking. And then on the right-hand side, you've got energy release. So energy release, just to kind of compound things in complication here, is that every notch up the Richter scale, you actually increase the energy released by 32 times. And so, going from a 3 to a 4, again, you're releasing 32 times more energy. So essentially, as we get up that ladder into those high, 6, 7, 8 earthquakes, the amount of energy is a lot. There's a couple just general things that can kind of happen in an earthquake. Liquefaction on the left there is when shaking, induces the soil to kind of liquefy actually and lose its bearing pressure. And so what this picture is showing exactly what can happen. You lose bearing pressure and the building can just sink. So there's pictures like this of damage that happens where an earthquake shakes, liquefies the soil, and the building just topples right over and loses its bearing. Obviously, a surface rupture. This is a vertical offset, so you're talking about, what a 6-foot vertical offset along this track. And there's also, of course, a horizontal offset at a surface rupture as well. Not all earthquakes transmit through to the surface like this. So you don't, always get this type of action. And then landslides are pretty self-explanatory. So in big terms, global terms, we are, everybody's heard of the Pacific Rim and the Ring of Fire, and this is the concentrated area where all of earthquakes, a majority of earthquakes happen across the world. In terms of California, we have the big Pacific Plate bumping into the North American plate and sliding. So all of us south of that red line, the San Andreas Fault, are slowly moving up to Alaska. We move about 2 inches north every year. So if anybody has really good genes in the family, you can become an Oregon citizen in a few million years. And on the right, that's an aerial photograph of the San Andreas Fault, which is kind of, I see these types of pictures and it just kind of makes me amazed. Actually, you feel like you're on such solid land, and there's pictures like this that kind of prove otherwise. So that's just one of many faults across California. We'll zoom into Santa Barbara in particular. So here's a few fault lines through Santa Barbara, and you can see they're kind of scattered all over. They're not all active. There's some are potentially active, some are not seen as active, but there are certainly some in the region that are currently active. What in geologists or seismic geology, anything within the last 10,000 years, any knowledge of ruptures within 10,000 years, consider an active fault. Here's a few more in Santa Barbara. So this is just kind of zooming in a little bit closer, and you can see, like Santa Barbara in general, all the topography that we see, the mountains, the hills, the mesa and more mesa, all of the topography that we see has been caused by long-term movement of the earth. And so some of those hills and valleys that we see are, what are in green and yellow, the anticlines and synclines of the soil and rock, and then red are faults that are kind of across Santa Barbara. And again, not all these are active. One that is active is the Mission Ridge Fault, which is just up the top of the screen, MSR. And the last known earthquake there was in the 1700s. And one of the kind of important takeaways here is that with all of the faults that are around Santa Barbara, all of the faults have a kind of a certain length, and that length and the potential for a rupture dictates how much, what size of an earthquake we can expect. And, with a length of, the Mission Ridge Fault, which is, say 10, 12 miles, that could generate roughly in the order of magnitude of like a 6.5 earthquake. There's other faults that are, off the screen down below and off the screen up above that also can, generate fault earthquakes in that same magnitude up to maybe a 7.5. And other things that are important for any of you that I know and I recognize some names is when you see me walking around with my wife, that right there, that star that just dropped on, that's my home. So we are close to some faults or potential faults. When you see me walk around with my wife, don't mention it. It's easier that way. That way she doesn't have to worry about it. So, historic Santa Barbara earthquakes. As we mentioned before, there's a ton of earthquakes happening constantly. What we're looking at is, essentially a heat map with the accelerations that can be expected. So red and pink being the highest, and then toning down into the oranges, yellows, and greens. This map overlays from USGS all of the earthquakes in the last month that are greater than a 4.5. So there was one that was, not terribly far away. And what also popped up onto the screen there is going right through Fraser Park, red line. That is the San Andreas Fault that we mentioned earlier. This is, I apologize for the kind of visibility of this, but you can maybe squint your eyes and look hard, I guess. But all those little dots there are all the earthquakes, I believe greater than 2.5 in the last month in the region. So you can see there's maybe 15 or so earthquakes that probably none of us knew happened. So going back to some of the older earthquakes that happened in Santa Barbara, we have the 1812 earthquake, and before anybody kind of jumps on my back for the photos not being of that, if you're like an architectural historian, correct, these are from more recent photos because not as many people had their phones out to document everything in the 1800s, imagine that. But what was around in that time were missions, across the coast. So up and down, from La Purísima in Lompoc got more or less completely destroyed. They actually picked that up and well, they then moved on to a new site. The Santa Barbara mission had damage, San Ynez mission had damage, the Buenaventura mission had damage. So kind of taking the swath of how much kind of damage and doing some kind of back calculating, I guess they found that this was in the order of the 7.1 magnitude. So the big one that we all know about here in Santa Barbara is the 1925 earthquake, and this is big for actually a couple of reasons. Obviously architecturally it reformed, the way we think about Santa Barbara now. It also was kind of one of the triggers to actually start considering seismic design in the UBC, the Uniform Building Code. So this is obviously the Hotel Californian. It's a very classic example of unreinforced masonry building with light, flexible diaphragms, and the heavy masonry just pulls away from the building. It's not well connected. That's something that we've identified over and over with, retrofit or suggested retrofits. These don't do well in earthquakes. And if anybody's interested in Saturday night and going on a deep dive and just looking at old photos, this is pretty easy to kind of get lost and just start looking this stuff up and seeing all these old photos. One of the one on the right here, I kind of like, it's telephone building, obviously braced by telephone poles, but it's just kind of, again, classic examples of unreinforced masonry that we've learned kind of time and again is not a great, durable, ductile, resilient building material. And unfortunately, other countries, we see, generally when you see, a lot of damage, a lot of casualties, it's this type of structure, and we just saw the same example last weekend in Haiti, one more time. But it's interesting kind of going back and doing this kind of look through. A lot has changed over the years. We've learned a lot, but at the same time, a lot's the same. Like here's the Red Cross in Santa Barbara helping out, and people living outside on the right-hand side in their tents, and you see the same action in current earthquakes and going back into the 70s and looking at what happened after Northridge. People, again, down there in LA were camping in tents. Coming forward a little bit, 1978, there was another earthquake that was off in the channel and kind of concentrated energy out toward UCSB to the west. So there was damage at UCSB. And there was, a freight train overturned as the tracks were deformed due to the earthquake. But majority of the damage was actually concentrated out toward Goleta. So now here's our California earthquake. So again, the bright pink line running you know, from the Mexico border all the way up to Humboldt County through Los Angeles and through San Francisco. That's the San Andreas Fault. And that's the one that you maybe even watched a movie about, action movie. So here's earthquakes in the last month that were greater than a 4.5. Same exercise with faults that are earthquakes that were greater than a 2.5. And then the same thing with earthquakes that are any size. Obviously, there's quite a few of them. So the first earthquake we'll talk about was this 1906 San Francisco earthquake. This is there's a number of kind of interesting and amazing things about this. You know, it was a magnitude 7.7 to 8.3, which is a really big earthquake. This was actually picked up and kind of back calculated because it was picked up on a seismograph in Germany, which also picked up the Loma Prieta earthquake, same seismograph, and they kind of backed out due to this change in amplitude what this earthquake was. You know, the fault rupture of this one was about 300 to 400 feet, you know, which from here to Mexico is about 200 or feet, I think it's miles. Here to Mexico is, you know, 200 miles, so 300 to 400 miles running, you know, just south of San Francisco up through like Marin and up north is a big rupture. There was an offset, a horizontal offset of about I think up to 20 feet. And there was obviously widespread damage. Building codes started to think about fires as a result of this because there was huge fire all over everything. We had the Long Beach earthquake, 1933. Now this one, you know, luckily hit at 5 o'clock in the afternoon because it damaged, you know, more than 200 schools, you know, either completely destroyed or severely damaged. So people obviously recognized that that would have been a huge catastrophe if this earthquake had happened, you know, 2 hours earlier when kids were actually at school. But this, you know, some of you doing DSA work, this was the trigger that started the Field Act, which then moved into the current Division of State Architect, which basically governs, you know, construction design of schools. 1971, San Fernando Silmar earthquake. One of the kind of good things that came out of this was we recognized that the work that was being done through the Field Act was working. There wasn't a lot of damage or significant damage at schools. There was, however, a lot of damage at some hospitals. So that, you know, made us kind of recognize that we need to pay close attention to more important critical structures. Loma Prieta, 1989. This is, you know, when I start to remember these, actually, I'll be around for them. This, I remember, you know, for infamously being a little kid and a baseball fan, disrupting the World Series. But this, you know, of course, you know, the Bay Bridge was collapsed, partially collapsed. There was, you know, numerous buildings like this, soft story damage, liquefaction in some areas, big fire again in the Marina district. Northridge earthquake, 94 again. This one happened, you know, at 4 or 5 in the morning while people were sleeping. You know, there was, you know, kind of widespread damage. You know, a lot of the damage kind of happened in soft story structures like this one on the left. We found out about the fragility of steel moment frames, which we previously thought were, you know, a well-designed system, but we recognize that there's been some weakness in that due to some of the kind of construction specifics. This parking structure at Cal State Northridge completely collapsed. luckily, again, it just happened to be, when no students were around. But this event kind of triggered when we look at recognizing kind of near source seismic action. Here's a quick look at big earthquakes over history, red being older, blue a little bit more frequent or more recent, and then green is most recent now. And then again, we saw this image before on the right, but then, looking at the amount of energy that was released, looking at Northridge is on there, Loma Prieta is on there, San Francisco 1906 are on there. Okay, so just real quickly talking about seismic design factors, we start to realize all of these different things are important. How much does the building weigh? What type of lateral system is supporting it? Where is it located? How close to faults are we? And then an importance factor as we kind of recognize the importance of those other things, or recognition that we need to take care of specific buildings, whether it's like a important infrastructure project, an emergent, medical office, or a hospital, or a ag building. So history of seismic design, we're going to kind of strum through this pretty quick. So 1906, San Francisco earthquake, 1933, Long Beach earthquake, 1935 UBC, and actually the 1927 UBC, which is just after what we mentioned, the Santa Barbara earthquake. 27 UBC was the first time we actually mentioned seismic design and start to think about it in terms of a weight and then designing for a portion of that weight as a seismic. So 1935, this was the first seismic map that we had, showing in red there, pink, zone 3, which would be the high zones. 1940, so we have an earthquake. Now, this is saying, up at the very top, basically that value of C is multiplied by your weight. So at this point, we're saying, 4% of your weight is what we want to design an earthquake for. 1940 is the El Centro earthquake, which is a big earthquake because that was the first earthquake that was actually recorded via seismographs in near source. So we learned a lot about that earthquake, and that recording still dictates a lot of design. 46, there was some changes of that. 1950s. So this value of C, kind of in that middle column there, that changes a little bit, but it's basically the same thing. We're multiplying our weight of the building times some coefficient that we've learned a little bit more, and we feel a little bit better about this equation. In 1959, we get the first seismology recommendations from the Structural Engineers Association, and they've been updating these to date. So this is the first time that the Blue Book was issued, 1959. 1960s and 70s, again, our kind of earthquake equation. I apologize for that image on the right, didn't come in quite how I was hoping. But the equation there, 14.1, V, that's your seismic force. Z, K, C, those are different factors that we're combining in to account for how much earthquake design force we should have. W is just the weight of the building. So we're evolving these as we're kind of continuing to understand. So 1971, San Fernando earthquake. Again, we're just evolving. It's that same equation that we just looked at, but we're starting to evolve that a little bit further, put in some minimums. Further into the 70s and 80s, we talk about more minimums and some importance factor now in there. And that's kind of a direct result of that Silmar earthquake. And again, you'll see, these forces are essentially increasing. 1985, stepping out of California for a minute, was a big earthquake, and there's a lot of unreinforced masonry and liquefaction, and that directly led into the 1986 California Earthquake Hazards Reduction Act, which then led into the hazards reduction that Santa Barbara did. So unreinforced masonry structures that in the 90s we went through. And if you go to San Luis Obispo today, there's plaques on buildings that say this is an unreinforced masonry building, and it may not perform well in an earthquake. 1989, Loma Prieta, so liquefaction and soft stories we paid attention to. There's where that Seismic Hazards Mapping Act, 90s, early 90s, UBC. So we, again, have kind of evolved to that basic equation of multiplying something by the weight and coming up with a value to design for. And then we come to the Northridge earthquake. The Northridge earthquake was really kind of a big change in terms of near source. So we recognize that being close to faults has an impact on the level of design forces. So again, you know, we've kind of evolved these equations, but the basics are still there. We're taking a portion of the building weight and applying it as a lateral force. And, you know, in the 2000s, you know, we've still had, you know, changes, and we'll see in just a minute here how this is kind of over. So now plotting our years, you know, our time across the bottom, and then C sub CS coefficient. That's what we currently call it, but that's basically the coefficient that we're multiplying our weight by. So you'll see it's directly proportional to the weight of the building. It's the force that we're designing for. So early on, we had no design forces, and then we have the 1925 just off here earthquake, Long Beach earthquake, and we realized, oh, we need to design for earthquakes. As we learn more, we start to design for higher forces, and you can see here I've kind of broken out. We've got blue line, red line. So red line being low seismic areas, blue line being Santa Barbara, or in more general terms, kind of a high seismic area, because as you kind of recall from that, the first map that we saw, we were all lumped into one big seismic design category, seismic zone. Now we would call it a seismic design category. So we've learned a bit more. Forces have gone up. That's the first blue book that I mentioned. So we designed for structure type at that point. And then we get a little bit further. Our forces continue to go up. We're learning more. You know, I kind of like to refer to this as kind of like a battle of man versus nature. You know, like we're learning more about nature and we're trying to adapt to it. And this is kind of the results. You know, and all you can ask is that we're learning more and more. But you can see a break there from San Luis Obispo. Then, you know, I think must have become a separate zone. Like it joined back up. And then we get some earthquakes in here, Loma Prieta, Northridge. We're kind of going up. And then actually this is kind of where we start getting a little crazy, and some of you maybe can recall in the past decade, seismic forces have been kind of going all around, and it really is a lot to kind of keep up with. But we then, you know, based on that Northridge, we do some, you know, near source and site specific reactions. So now all of a sudden, you know, Bay Area, San Luis Obispo, Pasadena, you can put in a specific location and identify what sort of accelerations you're expecting to see. And keep going, and oops, sorry, one last, I don't know if they'll do that. There we go. So you can see it's kind of jumping all over, which has to do with the seismologists and the recognition of different things that we're learning more and more about earthquakes, and there's a probability to it. You know, where a site in like a site specifically, you know, there's probability of earthquake happening from fault A, and there's a probability happening from fault B, and then C and D. And so all of the kind of probabilities kind of work into these accelerations that we are taking and using for design. But yeah, you can see how complicated it's gotten in the last, you know, decades. Okay, so again, just touching back on these, you know, weight is kind of an hugely important thing. The lateral system, you know, what is it, and how has it evolved? Where is it? You know, how close are we to a seismic source? Importance factor. You know, is it a critical structure? So lateral systems. We're just going to look real quickly at timber structures, just because there's a whole lot under this umbrella, and we don't have much time. And we do a lot of you know, residential buildings here in Santa Barbara. So in the 1900s, early 1900s, you know, there's not a lot kind of going on, right? There was no rules as to what to do. So taking a typical 1,800 square foot home, putting a roof weight on it and some walls, we get some total weight, and the building, you know, say it weighs 50 kips. We have a pretty low C sub S factor, which we saw was down at the low ends, you know, before we grew and grew and grew. So that, you know, gets you to be, you know, 2,000 pounds per side of this building if we distribute it out. So you're going to see maybe some lead-in braces, but, you know, not much special. And generally, sill plates, you know, were minorly anchored. You can expect not to see much. 1960s, we saw a little bit of development. We saw some increase in forces like we just walked through. Same weight of the building, increase in force. Now we're up to, you know, 3,500 pounds. And again, you might see some sheathing at this point, but more likely you see some lead-in braces. You know, there is some anchoring, but it's, you know, not to kind of current standards or spacings. There is some use of fold downs, but not widespread. So more recently, we're, you know, of course, using OSB and other systems if we need them on more unique homes. Same building, we now have, you know, up to 5.5 kips. We expect that there's going to be regular sheathing and hold downs and anchor bolts. And then, you know, finally, you know, kind of a current home, you know, we've gotten a little bit bigger, or with our shear wall length, the forces have gone up. You know, we're, you know, putting, of course, shear walls, hold downs, anchor bolts, the whole deal. And now, you know, we are here in Santa Barbara in seismic design category D&E, which is, you know, up over on the right where that height limit is called out. That's based on the accelerations. So as we kind of talked about the highly seismic regions, you get into design categories D&E. When you're in other areas, you can be in the lower seismic design category. But you can see here that, you know, light number 15, light framed wood walls, that's generally what we're using, plywood shear wall, right? So that's acceptable up to a height of 65 feet. Light frame walls with shear panels of other materials, those are not permitted anymore. So we are not even able to use those materials. Not that we would want to. So we've been in, you know, multi-story buildings now using plywood sheathing and multi-story anchor devices. But that keeps growing and growing, you know, now in like Seattle and more urban areas, you know, those buildings are going to 75 feet and 5 stories or 6 even of wood. You know, we're starting to use cross-laminated timber in terms of just kind of keeping with the wood theme. that's a potential replacement of concrete for some multi-use buildings, mixed use. Okay, so I got a few more minutes here. What to take away in kind of client discussions. So this is something that is kind of interesting in how it's implied, I guess. If we design something for a current building code, the implication may be that there, for a client or someone who doesn't know, is that there's not going to be any damage to the structure. We've designed this building for the current building code, so it's going to be perfectly fine. Well, the reality is that it's designed for life safety, and that goes into like a bit of economics and the reality of being able to design for something to be operational or immediately occupiable. So in an earthquake, we can expect that there's going to be damage to buildings. That being said, in typical residences, perform really well. There's a lot of redundancy in walls. There's a lot of actual ductility in things and dissipation of energy and nailed connections and things. But you can certainly expect to see damage. And so that's one of the things that is just important to kind of remember and think about. Another thing to kind of think about when talking about these types of buildings or new renovation project are known hazards. We've had this long history of all these failures, and they're all very similar, and we've learned the lessons, and applying them is kind of another thing. So unreinforced masonry chimneys, those are a couple pictures on the right of chimneys after the 2001 Nisqually, earthquake, which is in Seattle. Something to look out for would be like repointed chimney, where you can see that the mortar between the brick joints is fresh and new compared to something in the past. Just means that they put that chimney back up, when the better solution is to mitigate that a little bit more. In terms of residences, the typical kind of failure that we see would be, cripple walls. So cripple wall underneath the first floor. So maybe it's 24 inches tall or something to get under a crawl space, but generally those aren't braced as well as the building itself. So you're going to see movement down there, and you can have the house fall off of that. So that's a really quick and simple, easy thing to sheathe that underside and make sure that you're kind of supporting that first floor. And then another, is soft stories. And soft stories, we certainly have these in Santa Barbara. You can drive around and kind of look at them, the tuck under parking. But there are, locations down in LA, Santa Monica, San Francisco, where there's ordinances that you have to retrofit these, and you're given a, 5-year window or something to do. But it's something to certainly be aware of, because this is, something that we recognize and understand is a hazard. These are kind of big topics here, but in general, the triggering of seismic or gravity kind of improvements. So the rule is, if you're altering an existing structure and you're increasing the dead live load more than 5%, you need to justify the existing gravity system for existing or current loads. That may be, putting a roof deck on top of a garage. It may be, putting Spanish tiles on a asphalt shingle roof. Important thing to think is you can consider both dead load and live load. So if you're minimally increasing dead load, it may not kind of push that 5% trigger, but 5% is not a big number. So that's something to kind of be aware of, that, this action could force some increase. Now, the bigger thing, especially here in Santa Barbara, is lateral load, and the big dollars come into a renovation when we start to get into, seismic increases. So increasing by more than 10%. So that's saying the demand to capacity ratio of any element is less than 10%. If you can keep under that 10%, then you aren't forced to make improvements. Now, that being said, like we've seen over time, right, that we've understood more, seismic forces go up. So the existing building that we're looking at wasn't designed for a current, seismic system. So it may not be forced, but it could be a good idea to add some plywood sheathing. Now, if you don't go over this 10% threshold, then you could do what's called a volunteer seismic improvement, and that comes with another little kind of requirements. But in general, if you're increasing the weight, that's generally what happens. We add on a wing, and it increases weight to a given line, anything like that. And we want to, make sure we're, updating to the current building code. We're adding plywood sheathing, we're adding hold downs, goes into this, so what does it take to actually update a wall? So generally speaking, an older building, you're going to have a 2x sill plate with minimal anchors. And what it takes to update to a plywood shear wall is, anything other than 6-inch nailing, and we need 3x nailers or at panel joints and sill, which means you could use a double 2x instead of a 3x. So you'd be getting new studs every 4 feet to get the panel edges. You'd be getting new blocking in the wall, which there probably was nothing there to begin with. You'd be adding a 2x sill on top of the existing sill and adding anchor bolts along the whole length. And you'd be adding hold downs likely. Now, that's in my mind, that's where the big money comes in, is the concrete work and the hold downs. And as we've been evolving this seismic understanding, material understanding has kind of evolved along with it. And in the last 15 or so years, anchoring to concrete has just gotten a lot more difficult. And what it requires is that for seismic components, where the primary force is seismic, a hold down is exactly that. You can anchor to concrete, but that anchor needs to be ductile, or you need to design for an overstrength factor. And there's kind of a lot of things going on, but the gist of it is it can be really very difficult to get the capacities you need out of existing concrete, which sometimes means that you have to drill down and go through and anchor to the underside of the footing or supplement the footing to strengthen the footing. But that, I think, is kind of the most complicated part of shear wall updates. And this, this I would probably cross out that client discussions because this is kind of complicated, but something just for you to be aware of. And there's, as we've learned more, again, through the years, we recognize that there's these different types of irregularities in buildings, both horizontal irregularities and vertical irregularities in the lateral load path that complicate the design, that are sticking points for load concentrations or whatever it might be, and we need to pay attention to. And now the current building code gives you direction on each of these things. So it actually specifically limits some of these things as well. So in like seismic design category D&E, you cannot have a weak story, in the bottom, looks like shear wall with a little kind of eye in the middle of it. You cannot do that, which for good reason. This other one, a lateral offset, that's something that we see a lot in Santa Barbara. When you are going up with, the primary shear wall in the exterior of the building, and then stepping back and being inside.
Excuse me, Say.
So,
start wrapping up soon.
Perfect.
Not a lot of time for questions. Yeah.
Okay. So quick little sidebar on ACE mentoring program. This is a program that's in Santa Barbara. It's across the U.S. There's 70 affiliates, 10,000 students, 4,000 mentors kind of across the US. I did this when I was up in Seattle. We basically concentrate on getting high school students exposed to the disciplines of architecture, construction, and engineering. And we're kind of gearing up to start a kind of fresh, maybe remote year here. What it is meeting with students over the course of the year. You know, we do a real life-ish project, let them kind of get their hands on building materials, design materials, and help them through the process as mentors and have them give a final presentation. If you're interested, then, you know, there's, you know, you can get in touch with me, or Tara would be great. She can relay that, and if you want to be involved, and there's definitely different ways that you can be involved. That's it.
Great, thank you, Sage. So there's just a couple of questions in the chat box right now. The first one is, any idea what percentage of earthquakes cause surface ruptures? Any
idea of the amount? Well, it's not a large amount. I think it would go back to the, you know, the one image that was, you know, kind of a inverted pyramid almost, showing the amount of earthquakes. There's a ton of earthquakes that are very small in magnitude, and you're not going to probably get a surface rupture, you know, until you're into that 7, 8 plus, and there's just a few amount, and then it depends on how deep, you know, the earthquake is, and so it's probably only a percentage of those that are that size would actually cause a surface rupture. Okay, the next one is, the Bay Area has the San Andreas Fault right through it. Why is their CS value so much lower than Santa Barbara's? Yeah, it's a good question, and I think it comes down to the probabilities, and so because there's, you know, maybe one primary source of rupture, you know, like the San Andreas Fault, I think, can generate, you know, a larger earthquake than what would be in Santa Barbara, but there's more kind of potential faults that can deliver some sort of earthquake in Santa Barbara. And so I think that the probability is what plays into that. And so you're taking kind of probabilities of, you know, it's an earthquake is, you know, saying, you know, there's a 2% chance of this happening in the next 50 years. And so if you take all of those probabilities from all the different potential sources, I think that's what's leading to some of the discrepancies there. Now, I don't know that, I wouldn't say I'm convinced that what we're currently designing for is the final answer. You know, it's gonna evolve more, and I would not be shocked if those kind of came a little bit more in line. But that's where we're at right now. Okay, any more questions from the floor, or? Doesn't look like it. Well, Sage, thank you so much. And just wanted to also acknowledge the ACE program that you work with, and AIA Santa Barbara's worked with you on that as well. And it's a great program, so I encourage everyone to get involved with that. And just one brief announcement from us is that next week we have a meeting or webinar on PR and how for architects, how to get articles in magazines. It's by a local PR firm. So yeah, thank you so much, Sage and Taylor and Saifan, and everyone for attending. We'll see you soon. Bye. Thanks, everyone.